Okay, good morning. So you should have gotten the homework project number 2 grades, right? So if you or your partner hadn't gotten the grades, let me know. I'm telling the TA to give feedback even for people who get a 100 score. I think a lot of you got 100, but he didn't write anything if you got 100. And I would like for him to actually say what he liked and ways to improve and stuff. So hopefully the next iteration we'll get that squared, right? So this is the scores averages, right? So far we have earned 36 points of the 100, so like sort of a third in the third of the way through, and I don't know what to make of it. I think everybody's doing fairly good. I mean, I think if you look at 80 as sort of like a B-ish kind of line, there is no sharp drop off at any point. There's obviously there are few who, I think one of them got a 98, and so, right? It's kind of fairly smooth, except I think there's one person who's at 70 or something, and I need to see why they're at 70, either because they didn't turn in something or something, right? So if you think your score is like on the low end, we still have enough points to make up to go higher. So yeah.
So is this just like flat percentage of points? They're not a possible scaling, like ratios of what homework's worth versus everything?
Yeah, it's scale what, right? So this is the 36 of the final, right? We finished 2 modules, so yeah, it's scaled to up to a 36, right? And like I say, if you have any questions about your grades or if you have any concerns, talk to me soon, because it's a lot easier to deal with stuff before than after, right? In the past, students have volunteered to make up some homework assignment by doing extra work or some other means, but it's a lot harder if you come right before the final exam, because you don't have time to do the stuff and stuff like that, right? So we left off at the fragmentation in the memory management module, right? Do you have any questions so far in what we looked at? So one of the things I want you to pick up from the operating system class is, OS is a core course, and I think even more than other core courses, this is more important, because regardless of what you do, you're probably going to deal with some operating system at some level, right? And so, you need to at the least understand if some things go wrong, what may be going wrong in terms of you programming or in terms of like some understanding, right? So at the least, I want you to take away the big picture of what is happening, right? If you forget the details, that's fine. I'm not insisting too much on the details. So if you don't remember what LRU does and what FIFO does, that's sort of okay. But if you don't understand what memory management is and why it's important and what is the general parameters, it's a lot harder, right? So I want you to at least get that part, right? So don't get lost in the details. Remember the big picture, right? So one of the things that another reason to motivate, like why we should care about all this stuff is, suppose someone wrote a program right? Suppose somebody wrote this like blindingly simple program where you're initializing an array, right? And it's a 2-dimensional array, so they're going through row and column, right? And suppose these two were interchanged, right? Suppose you, instead of going through row-wise first and then column-wise, suppose you changed it to column-wise first and row-wise, right? Would that change your program results? In this simple case, right? It shouldn't change anything in your program, right? So what I hope to get through in the memory management concept is, if somebody says, I want to switch this stuff, you have to answer something based on what you learned from memory management, right? Does anyone have a sense of what would happen if you switch these two? Yeah?
Depends how the compiled program stores the data in memory, it could store it, so the columns are first or the rows are first. So you might have to skip around to different places instead of going directly in order.
So what would happen if you skip around a lot?
Then you would keep bringing different things into memory and it would get fragmented.
Yeah, that's excellent observation. That's the next few slides that we're going to go through, right? Depending on how you set this stuff, depending on how you go through the stuff, essentially it boils down to how the matrix is stored in memory, right? Matrix. So you have 0, 0, and then it goes on in some sense, right? One way you would go through the memory sequentially. The other way, you would choose this location, then this location, then this location, then this location, and so on across the. Actually, you would go this, 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 and so on, right? And if you keep skipping around, depending on how the OS is set up, depending on what the memory is organized, that could give you horrible performance, right? In the worst case, it can give you so horrible performance, you will notice it even for normal arrays, right? So those sort of things, regardless of what you end up doing in life, you got to know, because otherwise you don't understand it. Because from a program perspective, these are both equivalent. You can change the row, you can do row or column, but from a performance perspective, you want to understand how this memory management stuff works, because otherwise you are polluting the memory, right? So where we left off, we were talking about you making a request for a memory chunk of whatever size you choose, and we're trying to fit them into whatever available memory, right? So if the available memory happens to be big, and you first ask for, something of this size, I give you this, and then you ask for something, say this size, I give you this, right? And then suppose this is, let's say these three were assigned, and then suppose this was freed up. Then the next request comes in, you kind of assign it somewhere, and so on, right? So the key here is it'll give you whatever you ask for, whatever size you ask for. So if you ask for 1 byte, it'll give you 1 byte. If you ask for 1 meg, it'll give you 1 meg. So if you do that, you run into the problem of external fragmentation, where suppose like this was assigned, the leftover may be so small that nothing useful can happen here, right? So if the leftover happens to be like 4 bytes or something, then you don't get to use. So this is external fragmentation because it's fragmented. It's not being used for anything else, but it's so small that nobody else can use it. The applications have no idea this is happening, but only the OS can keep track of this, so it knows that some chunk of memory is no longer being used, right? If you wait long enough, it may solve itself, right? So if this is not being used, if one of these gets freed up, then it becomes larger and you can get to use it, right? Or you can think of compaction, where you move these stuff around. So you move this stuff around, right? Depending on how the systems are built, you may be able to compact, right? But in general, we don't like, so if you go with this model where you can ask for any size you want, every time the OS has to figure out if you can fit something, it has to find a free block, and it has to see if your request will fit into the block. So it has to do 2 calculations. It has to see if this block is free and the size of what your request is can fit in here. So it has to do 2 comparisons, right? And one of the things you have to remember is anything that operating system does is overhead. It's not what your program really wants. So you want to avoid the OS having to do this 2 checks. So you would like to reduce the number of checks, right? So can you think of a way you can reduce the checks to? So right now you have to see if you have a free block and if the free block is of the right size, right? How would you? Can you think of a way where you can cut down on the amount of checking you have to do? That's it.
Maybe you could check for the beginning and the end of a free block, and then calculate the size from that, and proceed from the end of the free block.
But it's still, so it'll still do the same amount of computation, right? Yeah.
You just have the operating system have set block sizes. So it'd have a limited number of blocks, and say, you asked for 10, I don't care, you get all 1,000, and you just go block sizes of 1,000 for memory.
Yeah, exactly. That's the notion of paging, right? So instead of giving you any size you want, OS says I'm going to restrict it all to same size, 1,000 or what have you. So if you ask for 1 byte, I'll give you 1,000. If you ask for 10,000, I'll give you 10. If you ask for 10,020, I'll give you 11, and so on, right? So that way, the OS only has to check if the block is free, right? If it's free, then it knows it's 1,024. It knows what it should be. It doesn't have to see what the bounds are, right? And we'll use this. I mean, so that's a technique that's so popular that it's used throughout the system. So when you go to file systems, you run into the same exact problem. If you ask for a file and your file size was 2 bytes or 2 megabytes, do you either get whatever you asked for, or do you get like a same chunk, right? And as you'll see in the file systems also, you do the same thing. You give a certain size chunk, right? So if you, let's assume the block size is 1,000, right? Which means that if you ask for 2 bytes, the OS will give you 1,000 bytes. Because it can't give you 2 bytes, because it only deals with 1,000 bytes. So it'll give you 1,000 bytes, right? Which means that the 998 bytes of this chunk which is allocated to you is not being used by, you could use it if you want, right? But it's not used by anybody else. And that's the notion of internal fragmentation, right? In the internal fragmentation, the process knows that it has extra 998 bytes. Nobody else can use it, right? If the process chooses, it can use it, right? It doesn't have to go back to the OS. If the OS, if it wants another 2 bytes, it can go back to the OS, or if it's a little smarter, it can use whatever it has, right? And that's what your malloc system call does. Malloc is a library call. So when you do a memory allocation, you don't actually go and ask the operating system for 1 or 2 bytes. You actually ask for a big chunk and then do the internal allocation yourself to avoid the internal fragmentation, right? So those are the 2 ways you waste memory, right? You either waste it externally, where you don't know the OS knows, or internally, where OS does not care what you do with it. It gives you whatever one size chunk, and you go with that, right? And since the internal fragmentation mechanism also allows you the OS to be simpler, most operating systems do use fixed size memory blocks, right? Memory blocks or data blocks or whatever, right? So once you have fixed size data blocks, what is the problem you will run into? What is the number one thing you would have to decide how to deal with it? What is the number one decision you have to do when you're using a fixed size chunk?
What size do you use?
Exactly, right? What size do you use, right? So what size should you use? What size should you use? So now we say anything you ask for, the OS will give you something of size n, right? It won't give you anything smaller than n. It won't give you anything larger than n. If you want larger than n, you have to give you multiple chunks of n, right? So what should this n be? What would you choose n to be? Do you choose n to be small, or do you choose n to be large? Or the typical operating system answer, which is depends. Right? What would you choose? Why would you choose a small size?
Cut down on internal fragmentation.
Yeah. So to cut down on internal fragmentation, right? So if you're really running low on memory, you would want to have small chunks, right? So it will cut down on internal fragmentation. But what's the cost of making it small?
More of them to keep track of.
Yeah. So now the OS has to keep track of a whole bunch of stuff, right? So if you cut down the size, let's do all the way to 1 byte, right? Which means that OS has to keep track of every byte of main memory, which means that application, whenever it has to ask for lots of pages, OS has to keep track of a lot of pages to be freeing lots of stuff, right? And the large is the corresponding corollary, right? If you ask for large blocks, you'll have a lot more internal fragmentation, but you don't have to ask the operating system as much, right? And so over the years, we used from 512 to 81, 5K, half a K to 8K size for these blocks, right? And next slides we'll see some of this stuff, but essentially these numbers, right, are not set in stone. It's basically somebody deciding that this is a good enough number for whatever particular machine you're operating on, right? Some of these may be restricted by your hardware because you have to use the memory management unit to give you some things. We'll see what those are, right? But these things keep changing depending on what machine you are, what happens with the future, right? So if you have a machine which has 128 megabytes of memory, or you have a machine with 4 gigabytes of memory, right? Your laptop you can buy with 4 gigs of memory these days, right? So if you have one of those, then you make a decision based on how much you have, right? So if you have 4 gigs of main memory, you may decide that you have such a lot of memory, you don't really care about internal fragmentation. You care about getting the OS out of the way. So you may choose a larger size. And if you have smaller, less memory, you may care about internal fragmentation, right? So these are parameters you can set either during compilation or using some ways to get into the kernel and tweaking parameters. You may have to reboot the machine, but these are stuff that if any of you go beyond the using your computer for just the way it was installed and tweaking the kernel, these are ways you can tweak the kernel, right? You can set up some parameters. So people sell these accelerator programs for Windows that if you run this program, it'll make your machine faster, it'll give you more memory, or it's advertised as whatever. And they essentially do this by tweaking these parameters, right? They advertise you to say, if you run this little utility, then you'll have a lot more memory left. They don't tell you that the cost of a lot more memory is your system will be running slower because now it has to keep track of a whole bunch of stuff, right? But and Microsoft or Apple or something would keep looking at what this number should be for typical machines in the modern era and keep tweaking it as time goes along, right? So that's the big overview of what paging is. And whatever we said will hold for when we go to file systems and stuff too, right? So the notion, in order to differentiate the notion of you asking whatever size you want and we giving you only the size that the OS wants, the first model is called segmented memory, and the second model is called paged memory, right? The same concept to understand. So when you get segmentation fault, essentially it's a throwback to the previous age. Right? So you should actually be getting page violation fault, not segmentation fault, right? But so idea of paging is you ask for something and the OS only gives you a fixed size chunk, and the chunk size usually is 2 bytes. I mean power of 2, right? Because it's all binary, so it's the power of 2, and it's usually 512 to 8K size. And if you go to larger memory and mainframes and so on, you may think of making it into larger size, right? So in order to keep the discussion clear, we define, let's say this is the physical memory and this is the logical, right? So now everything is the same size, so you no longer have these things of different size. So you refer to this as page and you refer to this as frame, right? When you say frame, you're talking about the physical memory idea of this concept. And if you're talking about page, you're talking about the logical address space name of the same concept, right? Do they both have to be the same? So the physical stuff is defined by the hardware, right? The chips which do the memory management. So you may not have much control over how big this thing should be as much as this one, right? So can you imagine where frame is smaller than page? Do they have to be the same size, or can they be of different sizes?
Make them the same size.
Should be the same size. But can you make them different size? Can you make the page smaller than frame? Regardless of this dumb move or something, right? Can you do it? Some of you look like, why would you think about doing that, right? But you could if you wanted for some strange reason, right? So if you make the page smaller than frame, so in your physical memory, you're allocating a lot more memory than what the OS would see, right? So your physical memory, you allocate 4K, but you only give 1K to the OS, right? And that's a really kind of stupid move because you're wasting 3K for no reason, right? What may make sense is the other way, right? If you have this higher and this lower, right? So let's assume that the frame size is 1K and page size is larger, right? Let's say 4K, right? Can you do that? Conceptually, not going into details, right? You could. I mean, essentially, whenever the OS needs 4K, it has to find 4 different frames to give to you, right? It could do that, and many times the OS will end up doing that, right? So it can actually make this page size larger by allocating a whole bunch of frames to you, right? It could do the other way too, but that's a fairly dumb move, right? Or it can be the same size, right? So now the OS only has to keep track of the frames, the pages, the frames that are free, right? It doesn't have to know what the size is because they're all the same size. So it knows that if you ask for a certain size of memory, how many pages that will map into, and it knows from the pages, it knows how many frames it has to map into. It has to find enough number of frames to allocate to your process, and you're good to go, right? So now that we simplified the notion that all the page sizes are the same, right? This gives us another nice benefit that we didn't have before, right? The benefit is when you have a logical address and you want to translate to a physical address, right? Before we had to add some offset and then add these values, right? And adding may be slower because adding, if you take the hardware course, it's always slower, right? But since all the logical addresses are in nice boundaries of 2 and of the same size, right? One of the ways we can do is we can somehow try to parse the logical address as a bit field and go from here to here in an easier fashion, right? And that's what you typically do. So how familiar are you with binary arithmetic and binary operations? You must be, right? But at the least, so if you have a pointer, right? If you have a address, right? So on an Intel 32-bit machine, it's a 32-bit address. On a 64-bit machine, it's a 64-bit or what have you, right? So you have an address, right? Let's say this is 32-bit wide, right? And you have to translate this into some other physical address, which is also, let's say, 32-bit wide, right? So you are aware that 1K is 10 bits, right? And 2K is 11 bits, and so on, right? And 4K is 12, and 8K is 13 bits, right? So if you have a page size which is, let's say, 8K, 8192, which is 2 power 13, right? Right? We can use this to say, within the 32-bit, the lower 13 bits, right? Separate this into lower 13 bits and the upper 19, right? 19 bits, right? Separate the address into these two notions. So the lower 13 bits should be the offset within your page, right? It's because it can address up to 8K, and this 19 should be defining which frame you are, right? So since these are aligned up nicely in a binary fashion, we can say this is the offset within your page, and this belongs to the frame number where you are. So when you move something, when you have to translate, you have to translate only this part, not this part. So whenever a logical address is being created, the logical address's lower 13-bit can be left as it is. So you can copy this entire 13 bits over here. You have to only map the upper 19 bits. And the upper 19 bits, you have to map it to where in the physical address space this happens to be. So you change from adding something to doing a bit operation where you replace this upper 19 bits with something else, with where the current frame is, and use the lower 13 bit, and you're good to go. Is that clear? Right. So having it as a power of 2 gives you this power to figure out what it is. So suppose you have your page frames. Let's say these. Let's say your page frame is 1K size, right? So how big would the offset be? Huh?
10 bits.
Yeah, so this should be 10 bits, right? And this should be
22.
This should be 22 bits, right? So essentially, you copy over the lower bits, and then you operate with the higher bits, right? So so you have to now keep track of this one, of the upper order bits, right? So when we do that, that means in the logical address space, right? Let's assume we are doing 1K pages, right? In the logical address space, I can have 0 up to 2 power 22 bits of logical addresses would have to be translated to a physical address, right? So somehow the OS has to know that any of the logical addresses you can create, all the way from 0 to 2 power 22 minus 1, right? So essentially you have 2 power 22 logical address frames that would have to be translated to a physical address, right? It may not be useful to you at all. So what is this number? Yes, it's 4 meg, right? So there are 4 million entries, 4 million possible logical addresses that you have to keep track of what they translate into physical address, right? And these logical addresses are per process. So that means that for every process, the OS has to keep track of 4 million different addresses and what they translate to, right? Now your particular process may not use all the logical addresses, but it has to know that if you use another address that is not allocated, that is not allocated to you, right? So it has to either keep track of what it is for you or that you don't have it, right? So this means that for every process, you have to keep track of 4 meg, right? So if I make this into 8K, what would that change this for 4 meg to? Now it becomes 2 power 19, right? Which is 512K, right? So that cuts down on the overhead. That cuts down on this particular table that the OS has to keep track of, and that's called a page table that we'll see in the next few slides, right? So there's a cost associated with the managing internal fragmentation, and that's this cost, right? As you make the page size larger, you can keep track of fewer things. As you make the page size smaller, you have to keep track of more of this. And for every particular memory location, you have to keep track of this for every particular process. So if you have a process which only needs like 1K, right? OS still has to keep track of 4 million entries or 512, whatever it is. It has to keep track of that much, right? And that can be pretty overwhelming, and there are techniques we use to deal with that. But that's the high-level discussion of what really happens, right? We have a few graphs to make it more clearer, right? So essentially, I have a CPU which generates a logical address, P and D, right? It's the physical and the displacement, right? So the displacement depends on what your page size is, right? So depending on the page size, we just copy it over. So in this case, the page size and the frame size are the same. So we copy over that bit, right? For the physical address, you have to have this page table, right? And which kind of tells you that if you're asking for a physical address P, right? And if you index it as a table, then that's the physical frame where it should be. So you replace those bits with the one you find from the page table to figure out what the physical address should be, right? And the key thing to remember is the page table is per process, and you have to have as big as what the logical address space is, and it's pretty wasteful, right? But this can be done very fast because now there is no addition; it's just moving bit fields here and there, and it should be faster, right? So to give you an example, So suppose you have a process over the left, and it has a logical address, and it's using like 0, 1, 2, 3, and 4, right? And if the page table for the corresponding process was like that, right? Which means that page 0 happens to be in frame 1, page 1 happens to be in frame 4, and so on, right? So this way, whenever the process uses the logical address pages, you use the paging table to translate that to the corresponding physical frames, right? And you have examples of larger frames are having the notion that each of the physical frames may fit different page tables, and essentially you do the same kind of a translation, right? So the OS now has to keep track of free frames. So if you ask for a frame, it has to keep track of a free frame. It knows all the free frames are the same size and allocates to you as you request them, right? So before allocation, when you have this set of, if you look at the top corner of the free frame list, you have like five frames which are free. After the process runs, the frames are allocated in some order, right, in the page table, and you have the free frames left, right? So now the OS does not have to keep track of keeping them all lined up in any fashion. Remember, when you're doing segmentation, we have to worry about best fit or worst fit or what have you. Here, it doesn't matter where it fits. You can put them anywhere in the physical frame because they're all the same size. It doesn't have to worry about keeping them contiguous or whatever, because they're all contiguous in logical space, but don't have to be contiguous on the physical space, right? So that's a real plus for machines. Yeah.
What are the blue sections then? Are those taken by other?
Oh, the blue sections are free. In this illustration, taken by others. We're not talking about those, but yeah.
So the gray are just the ones that this new process could use for its pages?
The color is kind of misleading.
Oh, okay.
You ignore the blueness part,
Okay.
right? Yeah, it looks like the blues are taken by some other process, but just because the 15 is gray doesn't mean that only this process can use it. Anybody can use that, right? So having this notion of pages and frames makes the operating system a lot more simpler because it has to keep track of whatever is free, and it has to keep track of these page tables and stuff, and it's good to go. It doesn't have to keep track of how, external fragmentation is completely eliminated, and the OS does not have to keep track of keeping them contiguous or moving blocks and stuff because it's all the same size, right? So we solved one problem by creating another problem, right? We solved the problem of having to manage all this stuff by having this notion of page tables, and now the page table is fairly big, right? So now the page table is fairly big that we have to figure out what to do with that, right? So let's assume that you have 4 million entries, right? So let's say 4 million entries of addresses, right, on 32-bit machine. That means this is 16 megabytes worth of table, right? So for every process, you have to keep track of 16 million bytes of page table, right? So this has, it has to allocate this table for every time a process is created. It has to keep them in the PCB, right? And you can't possibly hope to keep them in main memory, right? So you may have to do the same thing you do with the main memory. It has to be, it may be swapped in and out kind of stuff. And you also have to keep track of which is valid and all those things. So now you solve the problem of how do you manage 2 power 32 bytes of memory to how do you manage 2 power 22 bytes of memory, right? Even though the 2 power 22 is smaller than 2 power 32, it's not that much smaller, right? So we use a number of techniques to speed this up, and we'll see what those are. But essentially the problem here is if they do nothing, even your hello world program would have to have 16 megabytes of page table entries, right? Which are basically wasted memory, not being used by a program. It's OS keeping stuff, right? So one of the ways you speed this stuff is you still have the notion of a page table, right? Now you hope not to keep the whole page table in memory all the time. You have separate caches where things can still go fast, but you don't have to pay the cost of looking at the stuff. And the way we do that is through associative memory or TLBs, or translation look aside buffer, right? How many of you went through TLBs in your architecture 1? Actually, that's a wrong question, right? How many of you means like anybody who took the architecture class should have gone through TLB, right?
We just talked about it this semester.
Oh, this semester? Okay. So TLB is it's this really funky memory. So essentially it says that if you have an array of objects, TLB can tell you whether whatever you're looking for is in there in one clock cycle, right? So essentially, if you think of it as searching, right? So suppose you have a table with a whole bunch of, this is the key, and this is the value, right? If you have a table like this and you have to search through them using your normal programming techniques, you would have a loop going through and looking at each entry, right? So if you're trying to see if this key belongs in this table, right, you would have to look to see if the key matches this one, this matches this one, this matches this one, this matches this one, and so on, right? In associative memory, you ask the memory, does this key exist in this memory? And the answer comes to you in one shot, right? It's done all in parallel. So the answer comes in whether, yes, this particular key matches what you're asking for, and here's the value, right? It comes to you in one shot, or right. So it's an extremely fast way of looking up stuff in a table, right? And that's the translation look-ahead buffer is an implementation of the associative memory concept, right? And associative memory concept it goes beyond TLBs. I mean, it's also used in some programming languages, like languages like Lisp and all support notion of associative arrays, right? And so the key to all the stuff is the hardware implementation called TLBs, right? And TLBs are really cool and they're really expensive, right? So if you're taking hardware class right now, TLBs are very hard to build. So you can't make the TLB 4 megabytes or something, right? I mean, you could, but it'll be so prohibitively expensive. So you have a smaller TLB, right? So the idea here is the pages that are being used a lot, if you can keep them in the TLB, maybe we can do something, right? So the way so here's the example of so if you use it for our construct, so we have a smaller TLB, right? And we keep all the logical addresses as the key and the physical addresses as the value, right? So if I want to know whether this particular logical address, the page part you've seen before, and what is the corresponding physical address, if I can use it using the TLBs, then I expect to speed up. So the way I do that is something like this, right? So now you do these things in hardware, and you do these things in parallel. So remember before when you had the physical address bit, right? You look in the page table, and if the page table is there, you replace it from there, right? But when you do it in hardware, you do both of these things simultaneously, right? Where the lookup on the page table is typically slower than what you can do in the TLB. And in the TLB, you have the page number and the frame numbers. You only have the TLB is a smaller size, right? So you make a query on the TLB and start the request on the page table simultaneously. If there's a TLB hit, you cancel this stuff. You cancel the request to the page table, right? And you get the answer, put it into the physical frame, and then you move on. However, if the TLB hit was a failure, then you have to go through and get it from the page table and move it on. And the page table is now treated as any other regular memory. So you have page table somewhere. It could be swapped out, or it could be in slower memory. So if you're lucky, things will be in the TLB. And if it's in the TLB, then you should be able to do this translation fairly quickly, right? Actually, there's a little simple calculation to show what that is. So if you do a TLB hit, when you're studying TLB, they tell you how quickly you can find the answer, right? One clock cycle, or I think here they call it as epsilon clock cycle, right? So what is the typical TLB's access times that you guys were looking at in your class?
We didn't really, I don't know if we touched on that.
He didn't say how fast they were.
Okay. So it's usually not 1, right? Let's say 1.1 or 1.2, right? Which means that within 1.2 clock cycles, I know whether it's a hit or not, right? And you want the epsilon to be as fast as possible. And but the memory is slower, so it has to go to the memory. It takes like 10 or 20 clock cycles, right, as the processor gets faster. So when you do so here's a simple equation to see what would happen. So if there's a hit, right, so you have the time it takes to do the TLB, right, and so the alpha is the hit ratio. How many of the requests will go to the TLB? How many of it goes to the main memory? So if it's a hit, then the first component comes in, where the time to get something from main memory is the one part is the actual stuff where you have to go to the memory, right? Plus the small epsilon part, which is the TLB hit time, right? If not, you have to first lose. So the second component, you lose the TLB. You have to go for the main memory to get the page table, to get the physical address, and then you have to go for the actual data. Does that make sense? There are two components at the bottom, right? There's the 1 plus epsilon alpha and 2 plus epsilon 1 minus alpha, right? Alpha is the percentage of hits which are going through TLB. If you get hit in TLB, the first component kicks in, right? If you get into TLB, then you have to pay the cost of 1, because that's the time it takes for your logical, the contents in your logical address has to be read, right? So you can't avoid that. So it has to go to the main memory for once. But if you have TLB hit, you only need to pay the TLB time, which is very small, which is the epsilon. But if TLB fails, you lose the time for TLB, and you have to add the time it takes to read the page table entry and then read the actual memory. So it becomes 2 plus epsilon, right? So depending on how your TLB hit happens, you could really be going at 1 plus epsilon rather than 2 plus epsilon. And like I said, most of the modern systems, the time to go to main memory is 10 to something slower, right? 10 plus something, right? So you could really save. So it can either happen to be, let's assume epsilon is 1 for argument's sake, and or in this concept it will be 0.1, right? So the difference between the first one and the second one can be 20 or 30 clock cycles, which can be pretty significant. Your system can go fast or slow, right? So it's extremely important to keep track of stuff in your TLB, right? So when you go into when you talk to hardware folks, they would guarantee you that if you have TLB hit, your system can be very, very fast. But if you're not doing a TLB hit, then your program can be very slow, right? And TLB is a hardware concept. So TLB is filled and managed by hardware. So you have to keep track of, you have to make sure that the accesses you're doing could be a hit, right? And that's where the example program I gave you came into picture, right? So if your memory accesses that you're trying to do happens to be for page frames, so let's ignore the offset part, just the page frame part. If the page frames come in as 1, 2, 3, 4, 5, 6, for let's say first instruction accesses 1, second 2, second, third 3, 4, 5, 6, and so on, right? And if you have a TLB of size 4, right? What would happen? Let's say the TLB is completely empty, right? So now the TLB remembers, it pays the higher cost, but now it remembers that you accessed 1, right? Your next instruction you're accessing 2, so the TLB somewhere gets, let's say with the 2, right? Let's do a first in first out kind of policy, right? Then you do a 3, then you do a 4, right? And then you're trying to access 5, right? Which means that something has to go, and let's assume that this goes away, right? And then something has to go. So if your application is going through like this, your TLB is completely being wasted, right? Because you're not reusing stuff, right? Ideally, what you would like is something like this, right? Where you use 1, 1, 1, 1. The first time it's not in TLB, it has to be loaded in the TLB. The second one is already in the TLB, so you get TLB hit, right? And then so on, right? Or you can even use it as 1, 2, 1, 2, 1, 2. This is good, right? Because you have 4 entries. So your TLB can have 1 and 2, right? So it could have 1, 2, 3, 4, 1, 2, 3, 4, which is still good, if you do 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, this is bad, right? We'll see why it's bad later on, but practically this thing will keep trashing the TLB all the time because it's kind of wrapping around, and we'll see what this problem is called and how to deal with those, right? So essentially, that your TLB defines what your performance is. Your TLB and the TLB displays the replacement policy. TLB replacement policy is done by hardware, right? OS has no idea what the TLB replacement policy should be. The set of accesses which are coming through here is done by the programmer, right? The programmer is the one who is doing this. So the programmer could be writing the program as for row and then for column, or for column and then row. They can change the order, right? So depending on how you write the program, this is defined by the programmer. The replacement policy is defined by the hardware, right? The OS is in the middle. So if the application programmer does not want to change the program, you will suffer the consequences, right? If the hardware folks have a weird TLB replacement policy, everybody suffers, right? And that's why you need to understand how these things interplay, because from an OS perspective, it can't do anything, right? If you wrote a program which makes these accesses, you will pay the consequence. So that's why we need to understand from a perspective what those are, right? And we'll take up with this on the next lecture.